We are going to deal with chemistry. I think it is very important that before we start, you all gather your tools to do. Hello, grade 12s. Welcome to Physical Sciences chemistry session. As you know that we are going to deal with chemistry, I think it is very important that before we start, you all gather your tools to do chemistry. The first thing that I would like you to all have before we start the topic is to at least have your periodic table in front of you, because you cannot do chemistry without periodic table. My name is Tandiwe Uwane. I'm going to do acids and bases with you. Now, this topic, acids and bases, is the topic that was done previously in previous grades. However, in previous grades, we were not looking into the intensified reactions of acids and bases. So for grade 12 purpose, we are going to look at the mostly reactions of acids and bases. Now, these are the objectives of the lesson. We are going to define acids and bases according to Arrhenius and Bronsted-Lowry theories. We are going to distinguish between strong acids and bases, weak acids and bases. We are also going to look at concentrated acids and bases, diluted acids and bases. We are going to write down the reaction equations of aqueous solutions of acids and bases, identify acid-base conjugate pairs for a given compound, write down the reactions equations of neutralizations of common laboratory acids and bases, determine the approximate pH of the salts in salt hydrolysis, and calculate the pH. As I said that this topic is not done for the first time in grade 12, we also did this topic last year in grade 11, where we also look at some of the concepts that we are going to do even this year. Now, let's start and define acids and bases according to Arrhenius. This is the principle. Actually, we are going to look at this principle more when we are defining our acids and bases, more than any other definition of acids and bases that you know previously. Now, what are these acids and bases according to Arrhenius? Arrhenius says acids are substances that produces hydrogen ions in a solution. Meaning that, let's say we have hydrochloric acid. If hydrochloric acid ionizes into ions in water, we are going to find hydrochloric acid ionizing to H+, which is a hydrogen ion, and Cl-. So from this reaction, you can see that hydrochloric acid is an acid because it produces an H+. So hydrogen quickly combines with water molecule to form a hydronium ion. The second reaction actually is the combination with the first reaction. What hydrochloric acid does, it just gives away a hydrogen ion, and what will happen, because it is reacting with water, water will accept the hydrogen ion and form a hydronium ion. So that is why Arrhenius concluded by saying acids are substances that can produce a hydrogen ion when dissolved in a solution. So this is an example whereby hydrochloric acid was reacting with water and was giving away a hydrogen ion to water, and that hydrogen ion was accepted by water. Now, let's look at what does base do in terms of Arrhenius principles. The bases produce a hydroxide ion in a solution, meaning that for you to say a substance is a base, according to Arrhenius, a hydroxide ion must be produced. For example, sodium hydroxide dissociates into its ion in water. So sodium hydroxide is an example of a base. So what it does, it dissociates to sodium ion and a hydroxide ion. So the formation of hydroxide ion is an indication that sodium hydroxide is a base. This is according to Arrhenius principle. Now let's move to the next principle, because as I said that we are going to look at the two principles, which is Arrhenius principle and Lowry-Bronsted principle. What does Lowry-Bronsted principle say? Now, according to Lowry-Bronsted principle, Lowry-Bronsted looked at acids and bases and said, acid is any substance that can donate a hydrogen ion. In other words, acids are proton donor. What do we mean by a proton? Remember, hydrogen is an atom. And as an atom is having a 1 electron and a 1 proton. 1 electron and 1 proton. Therefore, when hydrogen loses an electron, because we all know that you will never lose a proton, especially in a chemical reaction. So it means when a hydrogen loses an electron, it will only be left with 1 proton. And as it is left with 1 proton, it is written as H+, to indicate that 1 electron from hydrogen was donated. Therefore, that is why it's referred to as a proton. So you must not confuse yourself to say, there was an instant where we were explaining that a proton cannot be donated, but now we are saying a proton can be donated. In this instant, by a proton, we are only referring to a hydrogen ion. So an acid can donate a hydrogen ion, and a base can accept that hydrogen ion. If you look at the example of this acid-base reaction that is written below, you can see that we have hydrochloric acid and ammonia. Hydrochloric acid meaning that it means hydrochloric acid can donate a hydrogen ion to ammonia, and ammonia becomes ammonium ion. Therefore, there will also be a chloride ion that is formed. So this is according to, so what is donated? The hydrogen ion, which is going to be accepted by a base. Therefore, we can conclude to say hydrochloric acid is an acid because was able to donate a hydrogen ion to an ammonia, which is a base. So hydrochloric acid is a proton donor, whereas ammonia is a proton acceptor. So this is according to the definitions that we get from Lorentz theory. Now, these acids, they are differing in terms of their strengths. I think we already know these acids are acids that we see normally in our daily lives. We know that we have sulfuric acid, which is used as a battery acid. And we have ethanoic acid, which we also find in vinegar. Definitely, when you look at the two acids, you will not say they have the same strength. Now, that is why we went further and tried to classify or to distinguish between the strong acids and the weak acids, the strong bases and the weak bases. Now, I am going to look at which acids are strong acids and why are they referred to as strong acids. From the definition of strong acids are acids that ionizes completely in water. It is very important to understand that these acids, they ionizes. Because most of the time, when learners are giving the definition of acids, because they've taken it from the Lorentz theory or from the Arenas theory, they will always look at the formation of the H3O+. The H3O+ will only be formed after the acid is ionized. So it means that acids, which are strong acids, they ionizes completely in water to form a high concentration of hydronium ions in water. So the hydronium ions, the high concentration of the hydronium ions is formed because the acid is strong acid and it has ionized completely. Now, these are some of the examples of strong acids. Definitely, I cannot write all the examples of strong acids, but these are some of the examples that you might know for you to understand what are these strong acids. Now, the first one is hydrochloric acid. The second one is sulfuric acid and nitric acid. Now, when you look at hydrochloric acid and nitric acid for an example, you can see that hydrochloric acid is having only 1 hydrogen, whereas sulfuric acid is having 2 hydrogens, and nitric acid also 1 hydrogen. I always say you can't give what you don't have. So, for you to give something, you must have it first. When you look at hydrochloric acid, for it to donate a proton, it means for the nature of having only 1 hydrogen, it means it can only be able to donate that 1 hydrogen. So therefore, when hydrochloric acid dissolve, it will dissolve in such a way that is H+ plus Cl minus. So what has happened? Hydrochloric acid has donated only 1 proton. And by donating only one proton, we refer to it as a monoprotic acid. So mono means one. This means that only one proton can be donated by a hydrochloric acid. Now, when you look at sulfuric acid, it's H2SO4, whereby when it dissociates, it's going to be 2H plus SO4 2 minus. Now, when you look at sulfuric acid, it is having that potential to donate more than 2 protons because it is definitely having more than 2 hydrogen atoms in its compound. Therefore, it means it can be referred to as a diprotic acid. So, naming of acid or classifying acid will depend on the number of protons that it can donate in terms of Lorentz-Bronsted theory. If the protons were now 3, like in terms of a sulfurous acid, it means now that acid was going to be referred to as a triprotic acid. However, the most emphasis for this here is mostly given to a monoprotic acid and a diprotic acid. Now, when you look at nitric acid, you can also see that nitric acid is having only 1 hydrogen, so it means it can also donate only 1 hydrogen. Therefore, nitric acid is also referred as a monoprotic acid. Okay, let's go to the weak acids. Now, when you look at the weak acids are those acids now that they also ionize. However, weak acids ionizes partially or incompletely. Now, the weak acids, because they ionize partially or incompletely in water, they will form a low concentration of hydronium ions, unlike when we were looking at the strong acids. And the examples of those weak acids are, they may be ethanoic acid and oxalic acids. Now, when you look at ethanoic acid, CH3COO4, one might be confused to say, now, if this is ethanoic acid, how many protons can ethanoic acid donate? Because we were able to look at the diprotic, monoprotic acid in terms of the strong acids. Now, as we write it as CH3COOH, the only proton that will be donated from this compound is the last proton. You cannot be able to take any proton or any hydrogen from CH3, starting from the knowledge that you gain from the organic molecules. These are untouchable hydrogens. So the only hydrogen that can be donated is this one. That is why it will tend to be CH3COOH or COO minus. And we are going to refer to it also as a monoprotic acid. So not that the number of hydrogens always determines whether an acid can be referred to as a diprotic, triprotic, or monoprotic. It also serves to say which acid or which hydrogen can be easily removed from the compound so that it can be donated to the next compound. Now, the oxalic acid and the nitric. So this is how nitric acid actually ionizes. And you can see that when you look back at nitric acid became H plus and CO3. The content that was left after the hydrogen was removed is less as compared to the content that will be left after the ethanoic acid has ionized. And therefore, that is why we are saying ethanoic acid is a weak acid because it ionizes partially. Now, let's look at strong bases. Strong bases, unlike weak acids, strong bases are fully ionic. So they need not to ionize in the reaction. Immediately when you put the strong acids in water, they just dissolve into their ion. So we don't say strong acids ionizes, but we say strong bases dissociate. They do not ionize. I know that there are some of the books that they normally confuse the two, or they use the two words interchanging to say they dissociate and ionize, or ionize and dissociates. It's not the correct way. The correct way is that because strong bases are fully ionic, therefore it means they need to dissociate in water. And what they do, they dissociate completely in water to form the high concentration of hydroxide ion. This is very important. Remember, according to the Arrhenius principle, Arrhenius is the one that says bases produces hydroxide ions. So as they dissociate, they will produce hydroxide ions in water. Then this might be the few examples of bases. And when you look at the reaction whereby sodium hydroxide as a base dissociates, you can see that sodium hydroxide dissociates as sodium ion and a hydroxide ion, meaning that it has dissociated completely into its positive and negative ion. Then weak bases, obviously, they will be the opposite of the strong bases because they will dissociate incompletely in water and they will form a low concentration of hydroxide ion. And these are some of the examples of weak bases. Now, if you look at ammonia, when it dissolves in water, according to this reaction, what is going to happen? Ammonia is going to be the base because it's an example of a base, and water will react with this base. What is going to happen now? Because ammonia is a proton acceptor, because ammonia is a base, it will not be able, when it reacts with water, to donate a proton. However, water will be the one that will donate a proton to ammonia. And as it donates a proton to ammonia, ammonia will become an ammonium ion and a hydroxide ion will be released. And this hydroxide ion is an indication to show that ammonia is a base. Ammonia produced an OH minus ion because it's according to the Arrhenius principle. I will always take you back to the principle because these reactions that we are going to do are the ones that are always referring to the reactions, the principles that we did before. Now, sometimes we must understand that acids and bases, they react with water. And as they react with water, obviously, their concentration will change. So the concentration of acids and water will always depend on whether there is too much water present or there is less water present. Sometimes there won't be water at all. Now, it is very important to understand the strength also in terms of the concentration, because the way they are concentrated or the way the concentration is can also determine the way the acid and bases can react. As we can see that one of the factors that affected the rate of reaction was concentration. So concentration definitely will affect the way the acids and bases will react. Now, what happens in terms of the concentration? The concentration, as we know, is the ratio of the amount of a solute to the volume of a solvent. In our case here, we are going to use our solvent as water, and we are going to see what is happening with acids and bases when the water is too little or when the water is too much in the acid or base. So we are always saying if there is there's no water in an acid or a base, or there is little water that we cannot even notice that there's water, we refer to that acid or base as a concentrated acid or base. Let me just take a little back view. When we were looking at strong acids and strong bases, there's sometimes this misconception of learners thinking that immediately when we are saying the acid is now concentrated, we mean it is now strong. There's a difference between strong and concentrated. Concentrated means that acid, whether weak or strong, it is having little water or no water at all. However, strong means acid ionizes completely or bases dissociates completely. So there must not be a confusion of the two words of concentrated and strong, meaning that ethanoic acid, as an example of a weak acid, we can make it to be concentrated. Hydrochloric acid, as an example of a strong acid, we can also make it to be concentrated. It doesn't mean that when an acid is concentrated, then now it is referred to as a strong acid. Now, the next word is when an acid is diluted or when a base is diluted. An acid, when we add water to an acid or a base, we must know that that acid or base is diluted. And we must also know the correct way of diluting acid. For example, when you are diluting an acid, you must know that you must pour acid into water, not water into an acid, because some of the acids are very much dangerous when you do the reaction like that. Now, these acids, as we have seen that according to Lorentz theory, they can donate protons, and those protons can be accepted by the base. Immediately, when an acid donates a proton, we are going to find that there are compounds that they are going to form what we call conjugate base. Immediately when an acid like hydrochloric acid donates a proton and gives to water, what is going to happen? That acid will lose the acid status and become a base. Meaning that when you look at this hydrochloric acid, as it donates water, as it donates hydrogen ion to water, water changes from being water and become a hydronium ion. So this acid and these chloride ions, they are now conjugate base. What are conjugate base? Conjugate acid-base pairs are compounds that differ by the presence of one proton. I think we have already explained what we mean by a proton. So when you look at HCl and Cl minus, you can see that the only thing that makes them to differ is only the hydrogen atom. So HCl and Cl minus, they are referred to as an acid-base pairs. Now, immediately when the water accepts the hydrogen ion from an acid, the water changes from being water and become a hydronium ion. And when you look at hydronium ion and water, the only thing that makes them to be different is only one hydrogen, because water is H2O and hydronium ion is H3O+. So here there are two hydrogens, whereas here there are three. So that is why they are saying the only thing that makes them is when they differ by only one proton. So they are referred to as an acid-base pairs. This is another example of acid-base pairs. When you look at this one, you can see now that here we have ammonia. Remember, in our examples of acids and bases, weak acids and strong acids, ammonia was one of the bases that was classified as a weak base. Therefore, what is going to happen here? When ammonia reacts with water, ammonia will, because of a base nature, will accept a proton from water. And when ammonia accepts the proton from water, and then it becomes ammonium ion. So ammonium ion and ammonia, what differs between the two is only one proton. That is why ammonia and ammonium ion are acid-base pair. So you need to be able to identify between ammonia and ammonium ion, which one is an acid and which one is a base, or which one is an acid and which one is a conjugate base. So here, water, after donating the proton to ammonia, the water became a hydroxide ion because it has lost one proton towards ammonia. Therefore, water and hydroxide ion are conjugate acid-base pairs. Now, if you look at the two examples that I've just given, here on the first example, water accepted a proton from hydrochloric acid. However, on the second example, water is now donating a proton. And then you ask yourself, what is happening with water? Is now water an acid sometimes, or is water a base sometimes? Yes. Water, it can act as an acid, it can also act as a base, because water is referred to as an ampholyte. Ampholites are those substances that can act as acids and bases. Where the situation needs water to donate a proton, water can donate a proton and become an acid. And also water can accept a proton and become. So water can act as an ampholyte. Ampholites are substances that can act as both acids and bases. Then this ampholyte water is not the only example of an ampholyte. There are other examples of ampholytes. However, as long as you can see a substance acting as both an acid and a base, you must know that that substance has an amphoprotic, actually they normally say amphoprotic nature. So it can act as both acid and a base. Now, this is an activity that we can look at and see whether we have recapped whatever that we're talking about, especially in terms of the acid-base pairs, because these are the major concepts in terms of accumulating easy marks in our topic acids and bases. When you look at the activity, they say indicate the conjugate acid-base pairs in the following equations. So when you look at equation A, we have hydrochloric acid reacting with ammonia, giving you ammonium ion and Cl minus. So from the pen that you are having next to you, you can start now by trying and identify which one is an acid in the first reaction, in the first reaction in terms of hydrochloric acid and ammonia, and which one is an acid in terms of ammonium chloride and Cl minus ion. Therefore, after identifying that, is then that now you can match them in terms of acid-base pairs. Like, let's take the first one. The first one is hydrochloric acid plus ammonia, giving you what? Ammonium ion plus chloride ion. When you look at hydrochloric acid, for it being nature of a strong acid, is a strong acid, and wherever it reacts with whatever, it will definitely be an acid, because all the strong acids, whatever they react with, they will remain acids. Unlike other acids, sometimes they change because of, like water, they change because of the nature of whatever that they are reacting with. Now, hydrochloric acid definitely will donate a proton, and immediately when it donates a proton, it becomes Cl minus, meaning that Cl minus, which is chloride ion, and hydrochloric acid are acid-base pairs. So if this is your acid 1 and it donated a proton and became a chloride ion, so this is going to be your base 1. This acid and this base, they look alike. They have some qualities, or they have some properties that makes them to relate. So what makes them to relate is the Cl, is the chloride ion. So the proton that will be donated to where? To ammonia. So ammonia is a base. However, already we have identified our chloride ion as a base 1. So because this is also a base, it means ammonia will be our base 2. And our base 2 must have an acid, and that acid will be ammonium chloride, and this one is going to be our acid 2. So this is how we identify the acid-base conjugate pairs. You must not even be confused. You just look at the number of protons of the reactants and you compare it with the number of protons of the product. As long as the number of protons differ by 1, it means that 2 substances are acid-base pairs. Now, we can also look at the second example, which I'm not going to do because of time, and also we need to define acid-base according to Arenas and Laurie-Bronsted theory and give examples. Remember, these principles are very important because they are definitions, and they are defining everything that you are doing. Since I started with the reactions, I've been using the 2 principles of Arenas and Laurie-Bronsted. So it is very important that you understand the 2 principles and you distinguish between the 2 principles, because the other one doesn't say what the other one is saying. So it is very important to know it. And because this is also an exam question, you will also be sometimes expected to define acid according to Arenas or Laurie-Bronsted, or base according to Arenas or Laurie-Bronsted. So you must be able to say who said what. Now, okay. We can also be able to calculate the concentration of acids and bases. And when we calculate the concentration, we will see whether the acid is diluted or concentrated. So this formula that you see here is the formula that we can use to calculate. It's an easy formula that is used to calculate concentration. And this formula is found in your data sheet. So the concentration is always having a unit which is mole per decimeter cube. So if you calculate concentration, you always need to make sure that the units are part of your answer. Now, the formula is written in two ways, but the two ways of writing the formula, it means one and the same thing. Let's look at the example that is on the board. If you have 30 grams of hydrochloric acid and is mixed with water so as to produce 375 cubic centimeter of solution, what would be the concentration of the solution? Now, all the information that is given to you is very important. Remember, from the formula of concentration, you know that C is equals to N over V, meaning that C is equals to N over V, meaning that for you to calculate the concentration, you must know the number of moles. Remember, N is the number of moles, and this one is the volume of the solute, of the solvent. Sorry. So, if you are given the mass, I always say, if you are given the mass and the molar mass, the information actually that the examiner is giving you is the number of moles. Remember, the number of moles are calculated as mass over the molar mass. Therefore, from the information about hydrochloric acid, we are given the mass and the molar mass. When we started with our session, I said, we are doing the chemistry session, and definitely you need to have your periodic table in front of you so that when we refer to the periodic table, because we will time and again refer to the periodic table, you must use the periodic table, and it's also going to be given to you as the data during the examination. Now, if you have 30 grams of hydrochloric acid, when you look at your periodic table, you will find that hydrochloric acid, SaCl, for you to be able to calculate using this formula, you need to find its molar mass first. So in terms of the molar mass, you know that we add the masses of all the atoms in that compound. Now, if it is the molar mass of hydrochloric acid, is going to be the mass of hydrogen plus the mass of the chlorine, the chlorine atom. Now, what is the mass of hydrogen? According to your, if you are referring to your periodic table, you will see that hydrogen, the molar mass or the mass or the atomic mass of hydrogen is 1. And the atomic mass of chlorine atom is 35,5. When you add the two, you will see that this will give you 36,5 grams per mole. So this is the molar mass of hydrochloric acid. Then, after finding the molar mass of hydrochloric acid, you can now use the formula of of N is equal to M over M, mass over molar mass, to calculate the number of moles here that you can be able to use to calculate concentration. So the number of moles is going to be the mass of hydrochloric acid. We were told that is 30 grams. And then the molar mass is 36,5 grams per mole. Then, after getting the number of moles, is then that you can go to this formula and calculate the concentration of this hydrochloric acid. Then, after calculating the formula of the hydrochloric acid from this, you will see that if the concentration is more than 1, it means, or is 1 and above, it means that acid is concentrated. If you get numbers like 0, something, a mole per decimeter cube, you must definitely know that that acid is diluted. I will never go further and do other calculations. However, I'm just trying to show you that sometimes you will definitely be needed to calculate concentration, because sometimes the examiner can give you an acid and say, is this acid diluted or concentrated? So the values of concentration will always determine whether that acid or that base is concentrated or diluted. Immediately when you say 0, something, it means the number of moles, in terms of the number of moles, were less. If the number of moles are less, the value will be 0, something. If the number of moles are more, it means you will get a whole number. So the whole number most of the time indicates that that acid or that base, it is concentrated. Now, the acids and bases, one of the properties of acids and bases that we have looked at in our previous grades, we know that acids and bases can neutralize each other. We know that when you are having a stomach acids, you need a base that will assist you to neutralize that stomach acid. And that process of a base, in terms of any kind of a tablet that you can use, is referred to it as a neutralization. So when acids and bases react, we are saying we are undergoing neutralization reaction. It's different from the reaction whereby acids were reacting with water. When acids were reacting with water, it was not a neutralization, it was just a dissolution, or it was aqueous solutions. However, this one is based on the reactions of acids and bases. Now, when acids and bases react, it is not always that you will get neutral substances. Sometimes the substances that you are going to get, they are not going to be neutral. It depends on the strength of an acid and a base at that reaction. For example, when we have a strong base and a strong acid, it is easy for you to get a neutral solution because the two are having the same strength. They are both strong. However, in terms of strong acid and a weak base, definitely the strength of the strong acid will overcome that one of a base. Therefore, you will find that instead of getting you a neutral solution, you will get a solution being acidic. So a strong acid and a weak base give you an acidic solution. When you look at the example here, like for example, the example of ammonia and hydrochloric acid, you can see that ammonia and hydrochloric acid give you ammonium chloride. Ammonium chloride is a salt. And that salt, for you to determine whether it's an acidic salt or it's a basic salt, you must firstly identify the acid, the parents, the acid that formed that salt and the base that formed that salt, so that you know that if it's a strong acid and a weak base, that salt must be acidic. However, you can also use the salt and make it to react with water to check whether that salt is acidic or basic. For example, if ammonium chloride reacts with water, what will happen is ammonium chloride reacting with water, it will definitely give water a proton. And as it gives water a proton, hydronium ions will be formed also with ammonia. Hydronium ions are the indication that this is an acidic salt, because we know that hydronium ions or hydrogen ions are only produced by an acid. So the formation of hydronium ions indicate that ammonium chloride is an acidic salt. However, when you look at the second example, okay, this one. When you look at sodium hydroxide with ethanoic acid, sodium hydroxide is classified as a strong base, and ethanoic acid is classified as a weak acid. Therefore, if sodium hydroxide reacts with ethanoic acid, obviously the strength of sodium hydroxide will overcome that one of ethanoic acid. And what is going to happen? We are going to have sodium ethanoate as a product and water. Sodium ethanoate is a basic salt because it's a salt that was formed when a strong base reacts with a weak acid. Now, it is very important for you to know whether a solution that is formed after the reaction is acidic or basic. And the only way for you to know that or to see that is by using an indicator. Not all acids that we use in the laboratory are safe. Actually, nothing in the laboratory that is safe. So you need not to use your senses to taste whether this acid is basic or this solution is acidic. Now, we are using what we call indicators. Indicators are the instruments or the substances that we use to check whether a substance or a solution is acidic or basic. Now, we have many different indicators. However, the most indicators that we are going to concentrate on are only the three, which is promethyl blue, methyl orange, and phenolphthalein. These are the indicators that we're going to look at mostly when we are looking at neutralization. Now, this table try to explain, because we are not going to use any indicator for any reaction. We need to use suitable indicators for suitable reactions, as we have done with the catalyst before. We are using suitable catalysts for suitable reactions. Now, these indicators, we are going to use them because of the nature of the reacting acids and bases. Now, when you identify that the reaction is about the strong acid and a strong base, definitely we are expecting the solution to be neutral. So the indicator that we need to use in that specific reaction is known as promethyl blue. And the pH is not actually equals to 7, it's approximately or closer to 7, because pH of 7 indicates that a substance is neutral. Then, when we are having a weak acid, and that weak acid is reacting with a strong base, definitely from the previous examples that we have looked at of ethanoic acid and sodium hydroxide, we have seen that when strong base react with weak acid, the solution will be basic. And the type of indicator that we are going to use is phenolphthalein. Phenolphthalein, the pH of that indicator is greater than 7, meaning that if the pH is greater than 7, that means that solution is basic. And then the last one, strong acid, when it reacts with weak bases, the solution will be acidic, and the suitable indicator for that reaction is methyl orange, and the pH of the methyl orange is less than 7. So these suitable indicators are very important for you to know. You will also use this when you are doing your experiment on titration, because on titration, you need, when you are titrating something or you are finding a concentration of something, you need to know first the type of acid and base that are reacting for you to be able to choose a suitable indicator. Now, we can also be able to calculate the pH. I've already explained that the pH can also identify whether a substance is a strong acid, neutral, weak base, or a strong base. In terms of the pH, I think pH is something that we also did in the previous grade. We know that strong acid ranges from the very low pH 1 to 3, and then we start by having the weak acids, neutral substances, weak bases, and the ones with the high value, because the pH ranges from number 1 up to number 14. So the one with the high value, they indicate that those pHs indicate strong bases, and strong bases that dissociates completely. Now, how do we then, what is this pH? pH is just indicating the percentage of hydrogen ions in a solution. That is why it is pH. The stronger the acid, the more it dissociates in water, or the more it ionizes in water. Stronger acid will form more hydrogen ions, or the concentration of more hydrogen ions, lowering the pH value. So meaning that if the concentration of hydrogen ions is high in a solution, then the pH value drops, is low. So the pH, when you see the pH being low, it's an indication that they are more hydrogen, or there is more concentration of hydrogen ion in that specific solution. Then we are using this formula to calculate pH for our acids and our bases. However, remember, the pH only indicates the percentage of hydrogen ion, not the percentage of hydroxide ion. So this is the formula that you're going to find on your data sheet to calculate the pH. The pH is equal to the minus log 10 base 10, the concentration of hydrogen ions. Sometimes these hydrogen ions can also be replaced with hydronium ions, because these two means one and the same thing. Then you can notice that in the formula for pH, there is a minus. So it is very important that when you write any formula, especially formulas that are given on a data sheet, copy your formula correctly, because any formula that we give in our calculation is always allocated a mark. Then we can calculate the pH. Now, if an acid is a strong acid, this is, I think it is very important and it must be emphasized. When you have a strong acid, we know that for the nature of strong acid ionizing completely, it means that whatever the ions that will be formed will have the same concentration of that acid. For example, if you have hydrochloric acid, and then hydrochloric acid dissociates, it will dissociate to H plus Cl minus. Now, what is important is when you know the concentration of hydrochloric acid, you already know the concentration of the hydrogen ion and the concentration, because it's 1 mole of hydrochloric acid react and then producing 1 mole of hydrogen ion and 1 mole of a chloride ion. So the concentration of hydrochloric acid will always be the same as the concentration of hydrogen ion, because hydrochloric acid ionizes completely. Also, when coming to the bases, because the strong bases also dissociates completely, it means that when sodium hydroxide dissociates, it will form sodium ion and hydroxide ion. Therefore, the concentration of the sodium hydroxide will be the same as the concentration of the hydroxide ion, because sodium hydroxide is a strong base. So this is only when you are aware that you are dealing with a strong acid or a strong base, where you can associate the ion, the concentration of the product ions. Now, when you look at the example here, you can see that, which is an example, hydrochloric acid is a very strong acid, it's a strong acid. So if you are told that they had calculate the pH and you are given the concentration of hydrochloric acid as 0.1 mole per decimeter cube, you already know that if they are telling you that the pH of hydrochloric acid is 0.1 mole per decimeter cube, that means also the pH of hydrogen ion is 0.1 mole per decimeter cube. This I will always emphasize. This is possible only when you are aware that that acid is a strong acid. So if you know the pH or you know the concentration of the hydronium ion, you can go straightly to your formula of pH is equals to minus log the concentration of H plus ion. Therefore, after substituting this, you will then just go straight minus log, and then immediately when you start substituting the value, the pH, the concentration brackets, because the square brackets indicates the concentration of hydrogen ion, we can make it the round brackets and make it 0.1. Therefore, the pH, you will find it as 1 if you look at your calculator. Then this pH, remember, it doesn't have units. You must never ever think that pH is calculated as concentration, because pH doesn't have any unit. So when you look at the pH of hydrochloric acid, you can see that the pH of hydrochloric acid was found as 1. Therefore, if the pH is 1, this is an indication that hydrochloric acid is a strong acid. Now, let's look at, okay, in terms of the bases, because our formula to calculate pH is only looking at the hydrogen ions, the concentration of hydrogen ions, we know that according to Arenas, bases do not produce hydrogen ions. However, bases do also have hydrogen ions, even though we didn't mention that also bases can produce, but at a very low instant, at a very small amount, because both acids and bases, they have hydrogen ions and they also have hydroxide ions. Some of the bases, they also have hydroxide ions and hydrogen ions. So if a base, we want the pH of the base, we cannot up straight go to the formula whereby we were using to calculate the pH of an acid. We now need to find the amount of the hydrogen ions in that specific base. Therefore, for you to calculate the pH of the base, we know that a base is fully ionic and it can dissolve nicely to its positive and negative ions. Therefore, we need to first find the number of hydrogen ion in that specific base for us to be able to calculate the pH of the base. Now, let's look at this example. For you to be able to calculate the pH of a base, you need to firstly understand the constant ionization of water. The constant ionization of water explains that water can react on its own, forming the hydrogen ion and the hydroxide ion. Therefore, as water can form hydrogen ion and a hydroxide ion, it means from water we can be able to find both the ions of an acid and both the ions of a base. Now, it is very important that the constant ionization of water is understood for you to be able to go and convert it to the pH of a base. Now, the constant ionization, Kw, which is the symbol for the constant ionization, is given the value 1 times 10 to the exponent minus 14. So for you to be able to find the number of hydroxide ions or hydrogen ion, you are going to be guided by this constant ionization of water, whereby water reacts with itself to give you an H plus, which is H3O plus, and OH minus. So in water, we have both the ions. So it is very important that this constant ionization of water is understood for you to be able to calculate the pH of a base. So let's say you are given the pH of a hydrochloric acid, not sodium hydroxide. If you are given pH of you are given the concentration of sodium hydroxide, knowing that sodium hydroxide ionizes completely, it means if you know the concentration of sodium hydroxide, you already know the concentration of hydroxide ion. The only thing that you don't know is the concentration of hydrogen ions. Therefore, the constant ionization of water, this Kw, will assist you to use this information to find the concentration of the hydrogen ion. Like this example. Let's say you are told that they say find the pH of 0.5 mole per decimeter cube sodium hydroxide. For the mere fact that sodium hydroxide dissociate completely, if the concentration of sodium hydroxide is given as 0.5, that automatically means that the concentration of hydroxide ions is also 0.5 because of the nature of sodium hydroxide being a strong base. Therefore, when you know the concentration of the sodium hydroxide ion, you can easily go back to Kw, which is equal to the concentration of H plus ion multiplied by the concentration of OH minus ion. Remember, the value for Kw was given to you as 1 times 10 to the exponent minus 14. Therefore, you can substitute 1 times 10 to the exponent minus 14, which is equal to the concentration of H plus or H2O plus. Let me just use H plus because I've started with H plus. Then the concentration of this one, which we already know, which is 0.5. Then from here, you can divide both sides by 0.5 by 0.5 and get the concentration of H plus ion, whereby the concentration of H plus ion was, I think it was 1.10 times 10 to the exponent. I'm not sure about the value. However, after getting the value of the concentration of the hydroxide, of the hydronium ion or hydrogen ion, is then that you can now start by saying, okay, so now because I have the concentration of the hydronium ion, I can use pH is equal to minus log the concentration of hydronium ion or hydrogen ion. And then whatever value that you got for the concentration of hydronium ion, you put it here. So the value for this pH, I know when you look at your calculator, it's going to be 13.7. 13.7 is a very high value. The high value of the pH, we know that it indicates that that specific base is a strong base. That is why it's having a high pH. These are other extra examples that we can use to calculate the pH of a base and acids. They say, what is the pH of a solution? With the concentration. So this is a straightforward question because already you are given the concentration of hydronium or hydrogen ions. So when you are given the concentration of hydrogen ions, you need not to stress. You just go to your formula sheet. You look at the formula for pH. You correctly copy the formula of the pH. pH is equal to minus log the concentration of H2O plus or H plus ion. We can use the H2O plus, we can use the H plus ion interchanging because they mean one and the same thing. Therefore, because you were given the concentration already, you can say minus log. Therefore, you substitute the value 1 times 10 to exponent minus 6. And I guess maybe the pH of this will be 6. And if the pH is 6, it means this is an acid. However, this is going to be a weak acid. Because remember, the value of the pH will always indicate the strength of an acid in terms of whether it's a strong acid or whether it's a weak acid. What is the pH of the solution whose hydroxide ions are 9.31 times 10 to the exponent minus 2 mole per decimeter cube? So on the second one, you are now given the concentration of the hydroxide ions. So we know that when we are given the concentration of the hydroxide ions, we cannot just go and say pH is equal to the concentration of the hydroxide ions. The pH will always be the concentration of the hydronium ions or hydrogen ion and not the hydroxide ion. So the first thing that you need to do, from this concentration of hydroxide ion, you need to check how many hydrogen ion are there. So you need to firstly find the concentration of the hydrogen ion by using Kw formula, whereby Kw is equal to the concentration of H plus ion multiplied by the concentration of OH minus ion. And then after getting that, you now have to say, okay, by the way, the value or the constant for Kw is always provided as 1 times 10 to the exponent minus 14. Therefore, you are looking for the concentration of H plus ion. Then the concentration of OH minus was given to you as 9.31 times 10 to the exponent minus 2. Therefore, after this one, we are going to divide by 9.31 times 10 to the exponent minus 2 both sides. And then we are going to find the concentration of the hydrogen ions. The concentration of the hydrogen ions. And then when we find the value of the concentration of hydrogen ions, is then that we can take the value and substitute it on the formula where we can calculate the pH. And definitely, for the mere fact that this was the concentration that was given to us, obviously they are looking for the pH of a base, and the value will be greater than 7. Then the next one says, identify the conjugate acid-base pairs. When you look at this reaction, you can see that we are given 2 substances as reactants and 2 substances as products. What we said is that the acid and its conjugate base differ by a proton. So when you look at this reaction, you can check which substances differ by a proton. Like, for example, if you can say, maybe you look at this carbonic ion, and this, you can see that they don't differ by only a proton. They differ by many things. There's a carbon here, there's an oxygen here, and whereas here it is not there. But when you look at this one, this hydrogen carbonate ion, and this carbonic acid, you can see that the thing that makes the two to be different is only one hydrogen. So when you look at the conjugate acid-base pairs, you know, you look at those substances that they differ with a proton. And in this case, we have HCO3 minus plus H2O, giving you H2CO3 plus OH minus. Now, when you look at these two, at this reaction, the reaction, you can see that HCO3, which is a carbonic ion, when it reacts with water, the only thing that makes them to be different with this one is one hydrogen. This one has more hydrogens as compared to this one. So therefore, if the other one is having more hydrogen as compared to the other one, it means this one will qualify to be an acid and this one will be a base. So what happened here? It means if this is a base and this is an acid, it means in this reaction, water here is an acid. And if water is an acid, this one will be a base. Now, this acid, let's say this is acid 1. This acid 1 is almost the same or is a conjugate base of this base 1. And because this is acid 1, it means this one is going to be base 2 and this is going to be acid 2. It is very important to understand that when you look at this acid-base reaction, you can see that this carbonic acid, H2CO3, it is having 2 hydrogens. And for it to have 2 hydrogens, it means it can be able to donate more than 1, which it means it can donate 2 hydrogens. Let's say the formula started with H2CO3. If we can just further this. H2CO3 can dissolve and become, or can ionize and become H plus HCO3 minus. When this is H2CO3 and we know that this one is an acid and it has donated a hydrogen and it became this, and this one is a base. Now, when you look at HCO3 minus, you can see that it is still having a hydrogen. So HCO3 minus can further ionize and become H plus and CO3 2 minus. Now, for the mere fact that here, this now is an acid because it has donated a hydrogen ion to give this base here. This can also serve as one of the examples that we have talked about, because I referred that water is not the only ampholyte that exists, but there are lots of ampholytes that exist. So a the HCO3 ion here is now an acid here, but it was a base here. So when you look at the property of this ion, you can see that this ion can serve as an ampholyte, because in one of the reaction, it was an acid, and in the other reaction, it was a base. Now, this is the solution of the activity that we have done. As I told you, that it means the acid that was formed with that pH is a weak acid, because the pH of that acid was 6. And also, when you look at the solution of the second example that we have done, we have seen that the pH that we have got is 12,97. I hope as we were doing the activities, you were also following up, because this is very important, and this is not just a difficult concept to understand. Now, when you look at these solutions, you can see now that for every formula in physical sciences, chemistry, if you give the formula, we give a mark. So there's 1 mark for the correct copied formula. You also need not to manipulate the formula. And then we also give 1 mark for the correct substitution, and also another mark for the correct answer, which you are not going to allocate any unit on it, because definitely if you can put a unit on pH, you are not going to get this mark for pH or for the answer. Then the one that we did for the base, as you can see as a solution, you have seen that now the only thing that we haven't done here, they didn't put the formula of the KW. However, it's either you get the mark for the formula of the KW, or you get the mark where now you have substituted the value of the KW. So it's 1 mark. Then what happened is that we are going to get another mark for the correct substitution. So this one is going to be a little bit at higher level as compared to the first one. And also for you to correctly identify the value of the KW from the data sheet, because of course the value of the KW will be given to you in a data sheet. You are also going to get a mark, and you are also going to get another mark for the correct answer. But look, on this one, as compared to the first one, you were only allocated 3 marks because the formula was given to you and the concentration of the hydrogen ion was automatically given to you. You were just substituting directly. But when you look at the second example, you can see that now you need to think further than just substitution. You need to firstly look at how am I going to get the concentration of the hydrogen ions before I can find the pH of that specific base. And then the last one is the one that we have all just did of the acid-base pairs in terms of the identifying of the equation. Okay, grade 12s, I hope this was the best lesson that you can use in terms of understanding the acids and bases. As I'm saying, you definitely need to look at the exam guideline, look at your textbook, so that you can be able to familiarize yourself with the way the examiners will ask the questions. And also in terms of the definitions, you need to make sure that you master the definitions as they are provided to you by your exam guideline, because that will assist you a lot in terms of answering the questions, because your definitions actually are the ones that are leading to most of the concepts that you are going to do on that specific topic. With so saying, thank you very much and enjoy your grade 12 class. Thank you.